Hello, everyone. So today I want to go over some of the important assignment questions. So the first question I want to go over is the question on the voltage plane. So imagine you had basically a voltage plane, and the plane has a particular length L, width W, and a thickness, uh, say thickness T, and one side is connected to a voltage source V, and the other side is connected to ground. So you have 2 points, 1 and 2. One is at V and 2 is at 0. So now the question was how to calculate the resistance, the equivalent resistance of this voltage plane, and also how to understand the current distribution in the cross section of this voltage plane, right? In this case, because the current distribution is going to be non-uniform, we cannot just simply use Ohm's law rho L by A to solve for the resistance, but rather we need to try to understand this from a more fundamental electromagnetic perspective. So what is the equation that basically governs the flow of current through this material, through this voltage plane of constant conductivity sigma? It is basically the charge conservation equation, which is del dot J plus the time rate of change of the charge density with time is 0. Time rate of change of charge density is 0. So what this means is that imagine you consider an infinitesimal volume, as I've shown here, and if you have a divergence in the current density from this volume, then the divergence basically causes a reduction in the charge density within the volume, which is another way of saying that charge has to be conserved, right? However, because the current flow here is a steady current is flowing, and therefore current has to be continuous, therefore no charge is actually building up anywhere inside the voltage plane, and hence the rate of change of charge density anywhere in the plane is 0, which implies that del dot J is 0. We also know that for a material of a uniform conductivity sigma, which is both isotropic and homogeneous, we can write the current density J as being sigma times the electric field inside this metal. And if you substitute this now in the original del dot J expression, you get del dot sigma times E is 0. And because sigma is uniform through the material, it can be taken out of this divergence, and therefore you get del dot sigma times del dot E is 0, which basically implies that del dot E is 0. Also, if you look at the other form of the Maxwell's equations, we know that the curl of the electric field is equal to minus rate of change of magnetic flux density. But because you have a steady current, the time rate of change of magnetic flux density is also essentially 0, and hence the curl of the electric field is also 0. From basic vector calculus, we know that the curl of a vector valued field is 0. Then the vector valued field can be represented as the gradient of a scalar field. And in our case, the scalar field, which is located at every point x, y, z, is also called as the potential field, which is basically the potential distribution, or also called as the voltage distribution. So if I now substitute this form of the electric field in the original governing equation, which is del dot E is 0, so del dot E is 0 becomes essentially del dot negative gradient of phi is 0, which becomes the Laplacian of phi is 0. So the governing equation that determines the distribution of the voltage distribution or the potential distribution inside this voltage plane is basically the Laplacian, subject to a certain set of boundary conditions. So what are the boundary conditions? So imagine now you had an interface where one side of the interface has a conductivity sigma 1, and the other side of the interface has a conductivity sigma 2. Now we can use a small pillbox. If you remember the pillbox approach from basic EM, so if you consider a small pillbox having an area element dA pointing in this way, and the height of this pillbox, or the basically the height of the cylinder tending to 0, then if we can write the divergence theorem, which is integral over the volume of del dot J integrate over the volume is just integral over the surface of J dot n cap ds. Because we know that del dot J inside this material is always 0 because there's no charge buildup, this becomes integral over the surface j dot n cap ds is 0. And if we write this explicitly for the pill box, imagine there's two current components. There's two currents. So one is there's a current J1 in material 1, and there's a current J2 in the material 2 across the interface. Then this basically says that the normal component of J1 times dA with a minus sign plus the normal component of the current density in the material 2 times dA should be 0, which basically implies that the normal components of the current density have to be continuous across this interface. Since we know that the current density is just going to be minus sigma times the gradient of the potential, because it's sigma times the electric field, and electric field is negative gradient of the potential. This essentially means that sigma 1 times the gradient of the potential, the normal component of the gradient of the potential in material 1 must be equal to sigma 2 times the normal component of the gradient of the potential in material 2. So now imagine you had an interface where on one side you have a conductivity sigma, but on the other side you have no material, which is basically saying that the conductivity is 0. Then under such a condition, the normal component of the potential, the normal component of the gradient of the potential inside the material at the boundary. So at this boundary or interface must be 0. That means that the equipotential. So if you draw, for example, the equipotentials must touch this interface at a 90-degree angle, because the gradient of this potential cannot have a normal component, but only can have a tangential component, which is also equivalent to saying that there is no current flow which is occurring. There is no current flow occurring in a perpendicular direction to the interface, because otherwise there will be buildup of charge at the interface, which violates our original assumption. So now, in order to solve, let's go back to the original problem, which was basically you had this voltage plane, and this voltage plane now, one side is connected to V, the other side is connected to 0, and we essentially, to solve for the potential distribution and hence get the value of the current density as well as the voltage distribution inside this plane, what we have to do is we just have to solve the Laplacian of the potential inside this plane, subject to the boundary condition that the normal component of the gradient of the potential at the boundary and anywhere on the boundary of this plane must be 0. So there's no normal component. So if we solve this, then we can get the potential. And if we can solve the potential at every location in space, we can just get the current density by taking minus sigma times the gradient of phi. And from the current density, we can calculate the current, from which we can calculate the resistance. So how would we do that? So the resistance is given by V over I. And we already know that the current in this material is continuous. So if you take any cross section of this voltage plane, the amount of current flowing must be a constant, which is I. So imagine I take a cross section here at the location LO2. So this is 0, this is L. Imagine this is x-axis, this is y-axis, and into the plane is z-axis. Then the current that is passing through this cross section at LO2 is just going to be integral of j dot n cap ds, which is going to be integral of j is minus sigma gradient of phi dot n cap times what is the area element there? The area element there is going to be dy dz. And if we assume, and this is a good assumption, because if we assume that the thickness T is much, much smaller, so remember that this is the thickness of the plane. If the thickness is much smaller than the width or the length of this voltage plane, then we can assume that the potential does not vary much. Basically, the variation of the potential along the z directions is negligible. So under such an assumption, that is, we are assuming the potential distribution is essentially uniform along the thickness direction, which is a good assumption if the thickness is very small, then the current just simplifies to minus sigma times T integral 0 to W of the gradient of phi dot n cap just becomes now going to be just x cap integrated over the cross-section, the cross-sectional length, which is dy, right? So now the resistance is therefore just going to be V over I. So it's V over this expression, which is minus sigma t integral 0 to w. And also remember that this gradient of phi is evaluated at the location L over 2, right? So it's just this times the gradient of phi evaluated at the location L over 2 dot x cap dy. And if you notice, what is 1 over sigma t? 1 over sigma t is essentially just the sheet resistance of this voltage plane. And therefore, the resistance is just going to be V minus V over integral 0 to W of the gradient of phi integrated at evaluated LL over 2, that x cap dy, this whole thing times the sheet resistance. So this expression is a very general expression, and it is essentially applicable to any kind of metal which has any kind of contact to it with any arbitrary current distribution. So this is a very general expression. So if you had any kind of metal surface and you were contacting it in any way and passing the current I through it, this current is obviously going to spread through this metal. But if you can calculate the Laplacian inside this metal subject to the boundary conditions, and then we use this Laplacian to create a cross section and calculate the current density at every location times the area and integrate it over this cross section, and we substitute that over here, then we can get the value of the equivalent resistance of this very complicated looking metal surface, a metal plane, right? So that is the general expression for the resistance. So now let us get a better intuitive understanding of how the potential distributes and how the current density looks like in this potential plane, in this voltage plane. So let me draw the voltage plane again. So you have basically the length L, you have the width W, and the thickness T, and here you have the voltage V, and here you have the voltage 0. So we essentially need to solve the Laplace equation del square phi equals 0. But since we know that the thickness T is much smaller than the length or the width, we can assume that the Laplacian del square phi just becomes the Laplacian in the xy plane alone of del xy phi. So what I'm saying here is that del square phi over del x square plus del square phi over del y square is basically much greater than the variation of the potential along the z direction, and hence this you just have to solve the two-dimensional Laplacian of the potential in this cross section, subject to the boundary condition that the normal component of the gradient of the potential at the boundary is 0. And so if you actually go about solving the Laplacian in the voltage plane, what would intuitively the potential distribution be like? So it looks something like this, like what I'm drawing here in green. So these are the equipotentials. And similarly, you have something here. So you have potential distribution, which looks something like this. Of course, this is a little exaggerated, but you can calculate for yourself exactly what it would look like. But you see here that the equipotentials must be normal at any point on the boundary, and which is required because of the boundary condition. And so now, for example, if this V was 1 volt, this could be 0.9, this could be 0.8, and similarly on the other side, it could be 0.2, 0.10, and so on. Now, what about the current density? So I plot the current density in red. Because the current density is proportional to the gradient of the potential, therefore, at every location, the current density must be perpendicular to the equipotential. So if I draw the current density distribution, it should essentially look something like this. And at every location, it is basically normal to the equipotential. And near the surface, it would look something like this. So you see how the current distribution is now going to be non-uniform. So in order to get a better feel, a semi-quantitative feel of what this current density distribution in the cross-section would look like. So let's take the metal, basically the voltage plane again. And now remember, one side is connected at V and the other side is 0. So if you look at the equation we need to solve, it's del square phi, basically in the xy plane, del xy square phi is 0. This is the x direction, this is the y direction. And if you look at the form of this mathematical expression, it's very similar to what you would expect as the potential equation for when you have 2 point charges which are located in free space. So it is a good analogy to consider these two voltage taps, 1 and 2, as just being 2 point charges located in space. And therefore, the electric field E at, say, some cross section L over 2 is just going to be V over the R, some distance R, where R is essentially this radial distance from this voltage tap. And so if, say, now this is L over 2 and this is the vertical height, which is some D, therefore the electric field E is basically going to be inversely proportional to square root of L over 2 square plus D square. And therefore the current density, which is obviously proportional to the electric field, is just going to be, current density is going to be proportional to 1 over square root of L over 2 square plus D square. So so let's consider limiting case where the length is much greater than D. And this is very similar to considering that the plane is very long, or the distance between the points 1 and 2 is so long that the plane now starts looking like a line. And under this condition, if you substitute this assumption in the current density distribution, J will end up being proportional to 1 over L. So what we find here is that if in this limiting case where the plane is now behaving as a line, as just a line conductor carrying the current density distribution, the cross section is going to be uniform, and the current density distribution, current density is just going to be inversely proportional to L, which is what you would expect from Ohm's law, because the resistance is linearly proportional to L, right? So this is just gives you the Ohm's law. However, if L is comparable to D, then the exact variation, the exact dependence of J on the distribution of the cross section would be given by this form. So if I look at this case where L is comparable to D, and I were to plot what is so I have V here and I have 0 here. If I were to plot what is the current density distribution in this cross section, so say I plot the current density here, magnitude of the current density distribution. So the current density distribution would have a peak value. If you see, the peak value occurs at D equals 0. So it has a peak value, J max, which is inversely proportional to L. And this peak value essentially falls as around 1 over D. And thus you notice that if you consider a certain cross-section of this voltage plane, the actual current that flows within this cross-section of the plane is just going to be the area under this curve. So you notice that if you make this plane wider and wider, end up consuming a larger area of this current density distribution. So beyond a certain point, increasing the width is not going to give you a significant increase in the extra current that is being carried by the plane. So after a certain point, if the width is made wider than that, it's not going to cause a significant change in the equivalent resistance offered by the voltage plane. So that was one of the questions that was asked in the assignment. There are also other ways that you can actually think about this problem. Another way is to consider, if you take the voltage plane again, another way to solve this problem is to divide this into a bunch of equivalent, basically a bunch of infinitesimal resistors, which are connected in series and parallel in a grid form like this. And this grid extends all the way to the other side, where you have the same kind of repeating structure. And so on. So this connected to ground and this connected to V. And in this case, you consider these resistances as some infinitesimal resistance, and then they are connected in series and parallel in this, basically this mesh, and you can find the equivalent resistance by using circuit theory. And this is another way you can compute what the equivalent resistance offered by this voltage plane is. And another approach would also be the splicing approach. That is, you take this region and you basically can say this region is extending from 0 to L. You can splice this region into a bunch of elements where each element has a length L over N. And within this L over N element, so say the current in this voltage plane, the tap is over here. The current can go this way, or this way, or this way, or this way. And then once it reaches the next splice, it can have multiple ways of going. And each one of these current paths essentially has an infinitesimal resistance given by rho times the length, which is going to be the square root of this L over N square, plus some vertical height y square over the thickness times some infinitesimal width delta. And then if you basically integrate this over dy and consider and add all the possibilities subject to the fact that the limit that n tends to infinity and delta tends to zero, then you would get essentially a functional integral that you can evaluate to solve for the equivalent resistance. This is another way to also think about the same problem. Of course, this is a much more complicated way, but sometimes having this kind of other perspectives how to solve the problem can be useful to get a good intuition. So that basically completes the discussion of the uh, distribution problem.